All right, here we go. Physics reaction number 36. This looks like it's a test review based on the name Honors Physics Unit Physics. Honors Physics Unit for test review, part 1. It's about 15 minutes long, so this must have been kind of like a lecture like the day before a test or something. And I got this with Honors Physics homework all spelled out, filter this week. So this is fresh. Here we go.
And welcome to the chapter test review. Okay, so in these videos, it's going to serve as a explanation of any questions that you feel like you need more than just the answer to,
Cool.
or maybe even the work. But first, check your answers if you haven't done so already, and certainly do not watch this entire video unless you feel like you really need to. Really kind of scroll along through it to the problems that you would like explained, and then please see me if you have any further questions on any of these.
So it sounds like this was something that he handed out, and maybe they could work the problems. And now this is maybe going over a review. The thumbnail for this video had what sort of looked like a worked problem. So I'm not sure if he's actually going to be working problems here or if he's going to be just explaining. But I really liked the way he framed the application of this. Is like, look, this is for you guys. If you've got this stuff down, great. What I used to say to my students is, if you flip through the book and you find yourself just going like this, yeah, flip, yeah, flip, then great, right? But if you flip through the book and you get to an image that you can't explain left, right, and backwards, then maybe read a little bit, check out some of my videos that I posted, that kind of stuff. But I think that the students who feel like, oh, it's uploaded, so I have to watch it. I mean, I guess that doesn't do harm, but it surely kind of makes it drudgery if they actually feel like they already know it.
Okay, so this is kind of a big topic, but a lot of these in the bottom half of these is just all applications of that second law and specific examples about it. Okay. And at the time of this recording, we're still going to be talking about the third law, and we're still going to be looking at two-body problems. Okay, so there's kind of some more things to come. So I'm just going to get right into it, and then, like I said, come see me.
So I'm always fascinated by blocking and spacing on these handouts, right? So usually teachers say, okay, well, I bet they need probably about this much space. And sometimes, of course, we've all noticed that we'll work the solution, like maybe we're posting a solution or something, we're like, oh man, that's a little tight. And I really am fascinated by students' reaction to that. It's like I should be able to fit it in here. If I'm not able to fit it in here, I'm doing something wrong. So what I started doing on my exams is I would just give the exam like question, and hand out just blank sheets of paper. But it was fascinating to learn that students, if it's not lined, I can't do it. I mean, there's just so many fascinating things about the way students work, the way students think. So let's watch and see if he's able to do this problem in the space provided. Let's see if he has to crunch it up at all. Let me understand this problem here. Okay, so a 5 kilogram thing, it's moving to the left. It's got a force to the right. Interesting. Oh, maybe that's the frictional force over there on the left. All right, let's see.
So here we have a 5 kilogram mass, and it's being applied with a force of 50 newtons. We know that there's got to be a downward force of gravity, and we know that there's got to be an upward normal force. Okay, so there's some additional forces. And then you're also told that there's friction of 9.8 newtons. So we have.
So I'm fascinated by the vertical forces. Let's see. I guess this applied force has a vertical component to it. So I guess we do need this. It's sometimes I kind of cringe, right? It's like, we don't need that stuff. Yes, it's true, but do we need to write it down? And so there's lots of people who say you have to write down every force. But in this problem, see, and I just caught myself, right? In this problem, my bias against, I'm tired of writing is, they need it because this has a vertical component. What's fascinating is that the frictional force is just given. So sometimes you need to figure out what the normal force is to figure out the frictional force, but in this case, we're just given it. Oh, but we're going to work it backwards. Let's see, because I think what's going to happen is a frictional force is then going to lead to the normal force. Nope, we're not given the coefficient of friction, so we can't do that. Because I was thinking frictional force could lead to this force, then we know what this force has to be, because we know what this force has to be. Yeah, let me think. Let's see. If we know this force, then we know the horizontal force of this. If we know the horizontal force of this, we know the vertical force of this. And so we know everything. Then we could do this. Yep, because it's got to provide whatever else is needed to keep this from falling. Ooh, okay. Yeah, and then you can get around to this. So wasn't that interesting? The way I read this problem, I didn't even notice this at the very, very end. Because I was thinking, we could just go boom, here to here. What? And so clearly we have to swing it around backwards to be able to get this connection here. Very, very cool. Let's see how he sets it up.
We have a frictional force to the left. So we want to know what is the net force. Okay, so we want to sum our forces in the x direction. So we know this one force that's acting at an angle has these two components. It has the x component and it has the y component of that applied force. So in the x direction, what we have is the x component of that applied force minus the force of friction.
So a little technology aside here, Screencast-O-Matic apparently. It's interesting that we can't see his mouse unless he's writing. And I have worked with some software that works that way too, and I've sort of gravitated to ones that show either a little yellow circle or at least a tiny little dot. The sound, the click, click, click is indicating he's writing something, because I was looking over there at the image, and then realized that he was writing over here in the center. I'll use my mouse. And so the clicking caught my attention. I had to look where there was new green showing up. And of course, once my eye was here, I stayed here and I was with it. But it's interesting that how much added would there be if there was a little yellow circle or a little dot, or frankly, even just an arrow, like my arrow here, to indicate what we should be looking at. Keep an eye for that, I guess.
Okay, and so I'm going to go ahead and just plug in, but this is F times cosine of theta minus that frictional force, which is 50 newtons times cosine of 20 degrees minus the 9.8 newtons. Okay?
Cool.
Value of 37.2 newtons. So that's going to be the...
Whoa, look at that. We do actually have this. So maybe it's that it follows his mouse but not his pen or something? That was really interesting. Let's go back and see if we can figure out when that started. No. 15 seconds? 20 seconds? Oh, maybe that's not what I think it is. Oh, never mind. I was doing the volume again. Let me click.
Some of the forces.
Let me pause, and then let me go back. Okay, so let's watch forward from here. When does that little mouse indicator show up?
Okay.
Just there. Ooh, with a yellow.
37 point.
Okay, so what's going on? When he clicked over there, it had the yellow. Maybe it was a mouse button, but it seemed like he was just using his pointer. Okay, well, that's a brief aside.
2 newtons. So that's going to be the sum of the forces in the x direction. Okay, so I'll circle that.
That's a lot.
And if we want to know what the acceleration of the block...
So, what do we know? So this is 50 newtons going down, and we're pulling the net. Oh, and this is 50 newtons up at an angle. Oh, interesting. So, it's not 50, it's whatever, 49.8 or something, but this is enough force when applied directly over the block to basically just barely lift it off the ground. And so now we've got, this is a pretty small frictional force, it's only 20%. So this thing is going to cruise along, because 20 degrees is kind of small. I don't think this is drawn to scale. This doesn't look like 20 degrees to me. But interesting numbers here. I was just talking to Tad yesterday. The video that I reacted to on Friday, he was saying that in his classes he just uses G equals 10. Come on, folks, just so that we can just cruise through these and really understand the conceptual relationship among these things. But we all know that this is no accident that the frictional force is 9.8. This is going to make things, I'm assuming, straightforward and easy at some point. So let's watch out for that.
Block is, well, of course, that's the net force divided by the mass. So that is 37.2 newtons.
Hang on a second. Did he verify it's not being lifted off the ground? I guess he didn't. We know that Fy is going to be less than Fx. Fx has to be at least 37.2 newtons. In fact, it's 37.2 plus 9.8. It's interesting, right? That technically he'd have to verify that this isn't being lifted up. That's my question for you. It's going to work out easy. This thing is definitely not anywhere near enough force to go up because this angle is so small, and 50 newtons straight up is what it would take to get it to lift off the ground. What do we think about that, right? Is it worth our time to do that kind of stuff with students? Is it worth it to make it a part E, like why didn't we have to do this, or stick it in here, I don't know, a new part B or something? I wonder about that.
Divided by the mass of 5 kilograms. And that works out to be equal to 7.4 meters per second squared. Okay. So now if we want to know what the value of the normal force is, what you can see is that we have a y component going up, we have the normal force going up, and we have the force of gravity going down.
By the way, look at these awesome, who cares about sig figs, right? We got 2 here, 1 here, 1 here, 3 there. Love it. So, sorry, maybe I should make a video about how much I hate sig figs. But I'll keep saying it. So I love this. I'm not being sarcastic. I really do.
And so we know that the sum of the forces in the vertical direction is equal to 0.
Mouse is still here.
And so we can write that the normal force plus the...
Hang on a second. Right here, he's going to get it. Right here, if he gets a positive value for the normal force, then, so this is the proof that it doesn't leave the ground. What's fascinating is, imagine we redid this problem where this was 500. If this was 500, this would be monster. This would be gigantic. But over here, we would get a negative normal force. Basically, we would need to have some glue on the track to keep it down there. So this here, part C, is where we're going to prove that it stays on the ground, because I'm guessing he's going to get a positive value for his normal force. Oh man, what a great follow-up question. Please redo this problem with 500 newtons instead of 50. What would the students do when they got here? Would they freak out by that negative number? Would they be able to know, oh yes, you got to fight against this. Oh man, I love that. That's so cool.
The y component, okay, because it's also going up, minus the force of gravity because it's going down, is equal to 0.
Mm-hmm.
So then that means that the normal force is equal to the force of gravity minus that y component, which of course this is...
Oh, the mouse didn't move. The page scrolled. I'm sorry, I'm so fixated on this. Man, it's so interesting. So he is about to get a positive number here. Let's see it.
This is mg minus f sine of theta, okay? And when I plugged in all my numbers, I got a value of...
He did run out of space.
1.9.
Hey, there's the mouse again.
Okay, so that's the value of the normal force.
Here's what I think is happening. I think he has one of these styluses that has a button. And I think that when he clicks somewhere with a button pressed, it literally moves the mouse. And that way he can for sure have his next text being written there. So he might have one of these tablets that's relative. So some tablets just map the entire rectangle of the tablet to the screen. And so if you're up here, you're up there. If you're down here, you're down here. But some are much smaller. And so you have to like recenter it with a mouse touch. So maybe that's what's going on. So here we have it, you guys, a positive normal force that's lifting up this mass. So this is all holding together. Now I'm really, really excited about this. I was thinking that this 9.8 choice was going to make this nice and clean, but now it's looking like it won't. Because basically it's the ratio of this to this, which doesn't look like a plain old normal number. Let's watch.
So if we now want to know what the coefficient of friction is, well, friction, you love friction because it's so fun, right? And so the coefficient is going to be equal to the frictional force divided by the normal force, which is 9.8
Oh
newtons
yeah, the
divided by
reverse.
this normal force of 31.9 newtons. And that works out to be 0.31
Hmm.
of a coefficient. Okay. All right.
Okay, so let's just stop it there. A few really, really fascinating things. This thing that I got hung up on the vertical actually showed up here. This excitement about a very, very well known and common number ended up not giving us anything interesting or well, like an integer or something, or a clear fraction. I think that's fascinating. Why would you choose 9.8 as a number if it wasn't supposed to make things cool? But maybe it's a distractor. Like, hang on a second. Well, if that's 9.8, then this has to be a 1 kilogram block or something. You know what I mean? Like that. That's really, really cool. I really liked how he just went after it, right? So we know some of the forces, let's go nuts. Some of the forces, let's go nuts. That's really the two main ideas here. This is really a definition approach, and over here, 7.4 meters per second per second. So let's see. In 3 seconds would be over 20 meters per second. Oh my God. Wait, let me do that again. In 3 seconds, I'd be over 20 meters per second. And 20 meters per second is like 50, 60 miles an hour. In 3 seconds? What? Okay, so this is 5 kilogram block. Okay, so a gallon and a half of milk. A gallon and a half of milk going 60 miles an hour in 3 seconds. Am I doing my math right there? Holy smoke and Joe. So this is a little bit slower than falling, right? And 3 seconds after dropping a gallon and a half of milk, it's cruising. I mean, it would hit somebody and it would hurt. These are really, really interesting numbers. All right, you guys. Well, very, very cool. I hope you have a great day. And remember, physics teachers are awesome.